We're going to take a look at another type of probability called binomial distribution. And you can see in the description here, binomial distributions are related to events where there are two possible outcomes. We normally refer to them as success and failure, but that sometimes confuses students thinking success means something positive. Success in this case really is anything that satisfies what we're looking for in this situation, right? So flipping a coin 100 times and counting how many times it lands on heads results in a binomial distribution, right? Flipping the coin in every flip is called a trial, and landing on heads would be the success we're looking for in this case, right? In that simple example of flipping a coin. So thinking about what is success, in this case, we're thinking about first generation parents did not go to college is our success. It's what we're looking for. It's not necessarily something good, it's just what we're looking for. So you'll see in a classroom of 16 students, right, using as a sample, we asked students which of their parents had attended college. Here is a list of the data collected, right? For each respondent mark those success. Again, looking at this here, we're interested in seeing how many students are first generation college students. So success in this case is that the parents did not attend college because of what I'm looking for. So you'll see there's 7 successes in this sample, right? Again, the number of who said their parents, neither of their parents had attended college, hence a first generation student. We define that success again as the parents who did not go to college. This is a first generation student. Failure in this case is parents who went to college, because we're not looking for that. We're trying to count how many are first generation students. It'd be really good if you could think of some other examples of your own of success and failure, right? Whether you pass the test or not, right? That's a classic success. Whether you get the job or not, right? These binary kind of options. That's a binomial probability. Now, when we examine situations like this, for something to be a binomial distribution officially, right? Because we always have these binary events, but for something to be a binary distribution, we have this check for short, if you can remember bin, binary, are the outcomes binary, right? Do you have only 2 outcomes? How do you define success and failure, right? Independent and identical events. So each trial is independent of each other, right? And the probabilities of each trial remains the same, right? It's about this idea, what is the probability of success? Does it remain consistent, right, the entire time? And then the number of trials. How many trials are there, right? It has to be a fixed amount for it to be a binomial distribution. Now, an important consideration, and it's a little theoretical here, is this idea of sampling without replacement in binomial. Well, when we do a binomial distribution, or when we're examining binomial distributions, we sample without replacement, right? But that doesn't satisfy our independence requirement. We remember in our previous lessons we talked about this without replacement. It changes our sample size. However, in many of these cases, we have this 5% rule. So if our sample size is less than 5% of the population, then we can assume independence, and then we can continue forth with our binomial distribution analysis. We can then use the procedures and tools that are aligned to binomial distributions, right? And so there's some notation we use. We use the binomial calculator and StatCrunch to do this, but we have some notations that are familiar that we use with a binomial distribution. Capital P, again, the probability. P is the probability of success, okay? Our little p there. But an S is success, F is failure, and you can see it's a complement, right? Because it's binary and so forth. So that's what we'll be doing as we move forward. And these first 2 examples here allow us to examine, really, are we looking at a binomial distribution? The first case is yes, second is no. We can see there is success and failure here, binary options, 35%, right? The trials are independent because we see the probabilities, right, are unchanged in these scenarios here. And then we have a fixed amount of attempts. So this is a binomial distribution. These would be the values that we'd be looking for. We're not calculating yet, but this idea of find the probability that the dolphin succeeds 12 times is what we would be looking for. Now we're going to be using, again, the binomial calculator. But to do that, we first have to identify our values here. And in this last case, this is not a binomial distribution because the number of trials is not fixed. You're flipping until something happens, right? Like in this example here, the dolphin was attempting the trick 20 times. It is binomial and they are independent, right? The probability is 50% every time, but it's not a binomial distribution because of the number of trials are not fixed, meaning they're not the same every time.